You're about to learn how to quickly prove this trig identity with just one formula, and stick around because there's a big trap here I want you to avoid on your next exam. Let's get started. When you see a problem like this, I personally don't like that there are four different trig functions here. I want everything to be rewritten in terms of cosine of x and sine of x like you see on the right. So I'm going to manipulate the left-hand side by rewriting secant of x as 1 over cosine of x and tangent of x as sine of x over cosine of x. And this is nifty because now when I look at the left, there's not just one, but two denominators that both are cosine of x. So why don't I just multiply both sides of the equation by cosine of x to really simplify them both? And not only that, but you'll notice then after the multiplication that on the right hand side, the numerator now is cosine squared of x. And this is useful because if you remember, I told you need just one formula, and there is a trig identity you can use here where cosine squared of x shows up. So remember that sine squared of x plus cosine squared of x equals 1, which comes from the unit circle as a very useful identity. But because we have cosine squared of x, we can simply just subtract sine squared of x on both sides of the equation, so that when cosine squared of x now equals 1 minus sine squared of x, we can substitute that right-hand side into the equation we were working with, which really just lets us have a lot more of a simpler time because everything now is written in terms of just sine of x. And if you want to learn more useful tricks, be sure to ninja kick that subscribe button so that you become a ninja that can see these cool tricks. Now, notice how with this equation, 1 minus sine squared is actually a difference of two squares, because 1 is really just the same as 1 squared, right? So when you have a difference of two squares, remember that you can then factor what you're dealing with. So when we factor 1 minus sine squared of x, we get 1 minus sine of x, all times 1 plus sine of x on the numerator. And so by inspection, you'll probably say, hey, Dave, we're done, right? Because you can just simply ninja kick the 1 minus sine x terms and cancel them out, leaving us with a final solution that says, hey, we got 1 plus sine of x on both sides of the equation, so we verified that the trig identity to prove is done. Well, yes and no. Remember, I told you there is a trap, because the problem with this is that if we don't understand the math we're working with and we're just trying to find the quickest solution, we may neglect the fact that, hey, we had 1 minus sine of x as a denominator in the work that we showed, along with cosine of x. And it's really important to understand that for this trigonometric identity we tried to prove, you need to restrict the domain, because there are cases where with 1 minus sine of x or cosine of x, if either one happens to equal 0, division by 0 is not allowed. And so what we're going to do now is we're going to go into the nitty-gritty details of trying to construct a domain in such a way where we can point out values of x that are not allowed. So because cosine of x, which was one of the denominators, cannot be 0, and because 1 minus sine of x can't be 0, we can use both of these and come up with that solution for the domain. Now, 1 minus sine of x not being 0 is the same thing as sine of x not equaling 1. So what I can do next is I'm going to draw the unit circle. And of course, the angles here are in radians. And because we're dealing with restrictions on sine of x and cosine of x as either having values that are not allowed of 0 or 1, we know those are values that happen to be points where the unit circle intersects the x or y axes. And so I just drew two of the points here, P1 and P2. You can follow along on your own as a homework problem and also evaluate points P3 and P4, which would be the remaining points of intersection with the unit circle and the axes. But for P1 and P2, what I want to do here is I want to write down what cosine of x and sine of x happen to be. So at P1, you'll remember that cosine of x is 1 and sine of x is 0, while at P2 at the very top, we have the reverse. Cosine of x is 0 and sine of x is 1. Now, what I want to figure out now is, okay, how do I construct a domain in such a way that gives me all values of x that are not allowed? The problem that most of us run into is when we look at the unit circle here, we are thinking in just a range of 0 to 2 pi, right? So the problem with that is sine of x and cosine of x are repeating functions. So we need to construct our domain in such a way where if I take any of those points that are restricted and I either add or subtract multiples of 2 pi, it covers those two. Because remember, if you start at one of these intersection points and you rotate counterclockwise or clockwise by any multiple of 2 pi, you'll end up at the same point and you should still restrict that value of x. And we're going to do that below. So if we go here now, I want to find all cases where sine of x equals 1. And as we can see above, right, sine of x is only 1 at not only pi over 2, but all cases of adding 2 pi multiples to pi over 2. So that's pi over 2 plus 2 pi plus 4 pi. And there are, of course, negative cases where you add negative 2 pi and so forth. Now, with cosine of x, it isn't just one point where cosine of x is 0. It's going to be whether you're intersecting the x-axis on either the right or the left. So what we'll notice now is cosine of x actually has a similar restriction in the domain to the sine of x equaling 1 case, because for cosine of x equals 0, this happens at also pi over 2 plus 2 pi, etc. But in addition to that, it further restricts us to cases where we cannot allow x to be 3 pi over 2 or any multiple of 2 pi added to that. So in other words, the cosine of x restriction here is a superset of the sine of x restriction. So we're just going to work with that one because it already covers the sine of x restriction case. So because cosine of x cannot be 0 at those values, remember that because we have pi over 2, 3 pi over 2, pi over 2, we should really consider writing all of these terms as an expression of a multiple of pi over 2. So like, for example, you have this pi over 2 plus 2 pi case right here, right? Remember, 2 pi is the same as 4 pi over 2. And you can work with a couple other multiples of 2 pi to see for yourself. But ultimately, when you rewrite this expression, it's the same as saying that cosine of x will be 0 at pi over 2, 3 pi over 2, 5 pi over 2, and you get the idea. And notice that the commonality with all of these terms is that the pi over 2 is always going to be multiplied by a constant that happens to be odd. Now, you got to realize that you can represent an odd number as an expression 2k plus 1, where k happens to be any number in the set of integers. So what this is basically saying is, given the cosine of x equals 0 restriction here, our domain is restricted in such a way where x can be any value except for a odd 2k plus 1 multiple of pi over 2.